Hi, I'm Jan Ozer. I'm here today with Hari Kalva and Velibor Adzic from Florida Atlantic University to talk about feature coding for machines and where their technology fits into the upcoming MPEG standard now in the later stages of development. Thanks for joining me, Hari and Velibor.
Thank you, Jen. Thank you. It's exciting to be part of your podcast, right? We have followed you. Finally, nice to be on your show here.
My pleasure. Thanks for the kind words. So why don't you gentlemen introduce yourselves briefly, let the audience know who you are.
Well, would you want to start, and then I can chime in?
Yeah, sure. So my name is Velibor Adzic. I'm an assistant professor of teaching here at Florida Atlantic University, and I've been working in the area of video and image compression for the last 10 plus years.
My name is Hari Kalva. I'm a department chair and professor of electrical engineering computer science at Florida Atlantic University. So I've been working in this video space, I would say, for a long time now, since 95, right after MPEG-2, we started implementing that video on demand system at Columbia, and we did one of our first demos. John, you may remember at Streaming Media East in New York. That's where we did first of our video out there, right? So I've been part of a number of standardization and video on demand type of efforts from that time, right? So including DAVIC, MPEG-4, MP4 file format, right? We did quite a bit of work in MPEG-4 and then a little bit of work in MPEG-7 later on, right? And more recently, we started working together with OP Solutions, right? They sponsored our ongoing work on VVC technology efforts. And more recently, again, continuing with collaboration with OP Solutions, we started working on machine-to-machine video efforts, basically. And we are actually announcing first time here, right, that we have just implemented a first real-time implementation of these new machine-to-machine standard called feature coding for machine, and we are excited to talk about it here today and share a little bit more about what we're doing.
Okay, well, good. Thank you for the introduction. Let's jump in. So I know the first couple of slides cover the key terms and acronyms. Why don't we start reviewing those to make sure our audience keeps up with all the terms we're going to be using?
Yes, so what our viewers should be probably familiar with here are these acronyms M2M video, which is just an acronym for machine-to-machine video. So instead of the traditional way of recording video, sending it out to probably human viewers, this is the framework where video is recorded and sent to the machine for analysis, and a human viewer might never look at it. So this can refer to anything that uses AI to analyze video, and we have proliferation of these areas lately: autonomous vehicles, robots, drones, smart cities, telehealth, agriculture, anything that basically involves camera recording and then analysis of that visual information. Features is another term that some of the viewers are probably already familiar with. This is basically if you have a neural network in a specific case, input to the neural network is going to be the image, but output of layers of the neural network is going to be these features or feature maps. So this is representation, basically visual information that's optimized for machine tasks. And then we have here inference, which again, neural networks usually are trained to complete some task. After the training is completed, they are ready to be put to the task, and the completion of the task, so seeing the new example by the neural network, is called basically the inference. Besides this, yes.
No, just add to that, right? So when you have a machine-to-machine video, right, you have a camera, essentially together with features, makes a very versatile sensor basically, right? So camera with a subset of features will allow you to do a number of machine tasks, right? So that gives you essentially a single camera that able to support a broad range of applications. And the features would depend on the application. Right? That's how.
Okay.
Further, there is a standard setting for the international standards where some of your viewers are already familiar with video and image standards produced by MPEG. But at the 141st meeting, the experts from MPEG initiated this MPEG-I, which is kind of an umbrella initiative, a project that is going to encompass all the AI-related activities within MPEG. The project was officially launched in April of 2023, and as parts of this project, there is a VCM, video coding for machines, which is going to be MPEG-I codec, designated as MPEG-I Part 2, which has video as input and video as output. It doesn't really deal with features. And then there's this FCM, which is our main topic today, feature coding for machines, which is going to be MPEG-AI Part 4 codec, and it gets feature tensors as input, and feature tensors are also produced as output, which are consumed directly by machines.
Okay. So Hari told us about all the wonderful codecs he's helped develop over the years. Why can't any of them work for this? Why do we need something different?
So if you look at traditional codec, right, they're primarily developed with human experience as an objective, basically. Right, so that means you care about pixels, you care about detail, so you care about increasingly high resolutions, etc., to meet application. Right, so when you begin to support a machine application, right, machines, they look at different level of detail to make a decision. So machines don't care about your 4K resolution, but a machine cares about having right embedded right amount of features, a right amount of video detail that allows it to make a decision, basically. Right. So for a machine video, if you can come up with an alternative representations and compression that retains those details that machines care about, right, without worrying about all the resolution, you have a big win. Right. You can scale systems, you can optimize it, you can support much broader range of applications. Right. So you have these efficiencies built into solutions like that. You could reduce bandwidth usage, right? You could reduce power consumption, and there's all in FCM proposes this model of distributing this compute across devices so that this encoding and inference could happen across multiple devices, right? So there is essentially new modalities of computation and services would be enabling basically to this, right? So a couple of key sort of almost built-in type of capabilities you come with these types of approaches are privacy. Privacy is super critical when you talk about public safety or monitoring applications, right? Nobody wants to be kind of on cameras, right? So on the other hand, if you convince individuals or public that, okay, you are not capturing a video, just sufficient feature details that don't have identifying information, you already have a privacy win there, right? So these are all the very interesting opportunities to that M2M allows to leverage, right? That you don't have in traditional video.
Why don't you walk us through some applications?
So there's a number of use cases, right? So one example, if you think about like a swarm of drones, right, that are performing a task, typically you may find it in a public safety or a defense applications, right? For example, a search and rescue is a common application. You may send out for a group of drones to go find a missing person, for example, right? So traditionally, if you do it today, what you had to do is for each drone, right, you had to capture a video. That video either has to be processed on the drone. That means drone may become heavy computation constraints there, or you stream all these videos to a central location, basically, right? So that means you need to have a higher bandwidth channel. If you scale it up and say instead of 4 or 5 drones, if you have a larger number of endpoints streaming a video, right? Streaming all that video back to a central location to analyze the video becomes sort of not a scalable option, basically, right? So that's an example where a M2M could work. If you have an M2M codec, you could have each drone essentially a more efficiently capturing those features and transmitting just the sufficient information to make those decisions, right? And architecture like FCM also enable interesting possibilities, right? Would it be possible for all these drones, right, to split a compute between them and do a collective decision, right? This types of collaborative computing is also possible through this M2M architecture.
Okay, so instead of the traditional one-to-many, where you do the full encode in one location, you're kind of splitting the encode to both reduce the processing and reduce the bandwidth consumption.
That's right. Yeah, that's interesting, right? Analogy, right? So in a traditional codec, right, you are targeting a consumer applications, right? You encode a video once and distribute it to play many times, right? You have a higher complexity video because you can bear the cost of it, right? You want the decoders to be cheap. In these types of M2M, these are primarily real-time type of applications, right? Where a large number of endpoints, right? So there is a many to many or many to one type of a scenarios, right? So then you want to leverage the compute of the many, right? So that way, splitting a compute allows you to scale back. Otherwise, instead of a camera capturing being a simple sensing device, right? It can also offload some of the compute there to gain the benefits of it.
Because you're not encoding the video to look good, you're encoding it to access the features. And if you don't have to encode if, that much to access the features, then you save a lot of processing power. So
That's
it's
right.
not
Yeah, you can optimize feature extraction, right? So you don't have to deal with again 4K or a high resolution video that you traditionally do, right? You may be able to, depending on application, subsample it and deal with a much smaller resolutions without losing your task performance.
okay. Thank you.
So this is another really very rich area for these types of M2M use cases is these autonomous vehicles type of cases, right? So that is this technology is still at infancy, right? They're still getting deployed. Trials are, we're beginning to see trials of robot taxis, etc., in different locations. So one interesting thing is all of these vehicles, right? Have a large number of cameras that are used for monitoring, for uh, uh, to recording, for essentially to continue to improve the systems, etc. Especially if you look at even fleet of trucks, right? The record roads, auto truck, autonomous 18-wheelers type of things. They even have more cameras to monitor their surroundings for both navigational purposes, right? For recording purposes, etc. So all this consumes huge amount of data, right? So when you deal with that amount of data, you no longer can afford to have traditional streaming, traditional video mechanism. So it's a very optimal use case for this is a M2M type of codec, right? Like FCM would nicely fit into this, where you would from each of these cameras instead of streaming a pixel streams, you extract features and more efficiently share. In a number of, as the fleets are deployed, a number of cases, right, you may want to make a remote decision as to how some of these machines operate. Remote assist is another use case people are thinking about, right? In those cases, streaming features will overall improve your fleet efficiency, right? Navigational uh, performance, right? All of those benefits would come in as well. Um, let's see. So if you look at, we talked about how traditional codecs work on compressing pixels and how machines are interested in features, right? So this slide sort of captures uh, how a machine sees, right, using in this example of a object detection and segmentation task using convolutional neural network, right? On the input frame is a video on the sensor and a camera end, right? So instead of transmitting a video, is there a more efficient way of capturing features within this frame to the remote end base? right? So if you look at a currently used object detection, it uses features what essentially looks like a grid on the right hand side, feature maps here, right? So essentially each feature map is a single feature map channel, output of a convolutional kernel of a CNN, right? So all these features together contribute to detecting a airplane. So it turns out uh, these feature maps are very robust, right? That means you can quantize them, truncate them, and you still have a sufficient information to detect a plane, right? So uh, in FCM type of a scenario, a picture is converted into a set of feature maps which are compressed, transmitted to a remote end where the detectors will use that feature maps to compute and detect an airplane basically, right? That sort of captures, it goes to show the type of information that machines need to perform a decision, right, is very different than what human eyes are used to, right? On the uh,
So what's happening here? Because typically we view video as a streaming type event, linear, and here we're seeing one image getting chunked up into say 40 images and then 4 images. So what's happening here?
so for each image here, right? So it is this is an example of a image where a object detection is happening, right? Uh, uh, Using a convolutional neural network, right? This convolutional neural network extracts a set of features, right? It's called essentially when we say a feature is we are highlighted here a single feature map channel, right? So uh, from this, each feature map channel is essentially capturing a different aspect of your different set of features from this airplane base, right? In the end, only a subset of these channels will have information relevant to detecting that it's an airplane, right? So that means as you process the features, you can identify which subset of these feature maps or feature channels are most relevant, only retain those and throw away remaining those, right? So it's similar to where in a traditional video codec, you throw away higher frequencies where people may not be interested, kind of discern or make out, right? In a perceptual sense. Same thing from machine perception sense, you retain just the features that your machine needs to make a decision, right? And then throw away the rest. That's how you gain a compression performance, right? You can. That's one way to look at it.
Okay, thank you. So why don't we review how this is different from traditional encoding?
Velibor, you want to go over this way?
Yeah, sure. So traditionally, right now, if you go out and want to implement a scenario where you are going to monitor something or analyze certain visual feed, the way that you would do it is you would have this, let's call it edge device, which is recording the video. The video would be compressed then and transmitted in a traditional codec bitstream to whatever is the central basically server that is processing this video. Video would be decoded and then it would be fed through the full convolutional neural network, which would give you at the output detections of the objects, let's say, if the task is object detection. So that's a traditional, or what is called in the field a remote inference, because the inference is happening remotely from where actually the video is captured. In the bottom part of the image here, we have now what's called a split inference. So the idea here is that instead of encoding the whole video and then sending it traditional way to the decoder, decoding the video and then feeding it through the complete convolutional neural network, you can split this convolutional neural network at some point. So usually these neural networks have many layers, and output of each layer, like we said before, is this set of features or feature maps. So instead of using input video and output detections, you can use input video and then this output of the, let's say, second layer in this neural network is going to be the feature maps, which are then encoded using the FCM encoder, sent to the decoder, decoded by FCM decoder, and now the task network on the decoder at the central unit only needs to pass these features through second part of the neural network to get exactly the same detections it did in the remote inference scenario.
Okay, so you're encoding once on the device, and then you're sending it to the server, and then you're encoding again there to access the features. And it
Right.
what's the comparative load on the encoding side? Are you doing it twice? I guess you're doing it twice in both cases, but how much are you cutting encoding by doing the split inference?
So the idea here is that for the split inference, the idea is that in the remote inference, you will have a traditional video encoder here that is going to encode the full frames, let's say 1080p video, and then send it to the decoder side. For the split inference, the original idea was that FCM encoder can be much simpler than your traditional hybrid video encoder because you're dealing with features which don't have really such a rich statistical structure as a natural video. So the idea was that this encoder is going to be much simpler than the regular video encoder, and it's going to pay basically by itself for having this additional burden of neural network part one of the first couple of layers of the neural network. Now, right now in the FCM, as we will probably discuss in the following slides, the part of the FCM encoder is a traditional video encoder. So the way that FCM right now is achieving efficiency is by pre-processing these features before it feeds them to the traditional video encoder. And as we will see, instead of encoding the regular full size 920 by 1080p video, we are encoding actually the frames that FCM is currently encoding is the frame of these packed features in the resolution of 288 by 192 pixels, which is significantly smaller. So the complexity overall is on par with the traditional video encoder. And then the decoder again is much simpler because of the much smaller size. And instead of running the whole convolutional neural network on the decoder side, we are also running only the second part. So the idea here is that in traditional video coding, you will encode once and then transmit to maybe millions of viewers. So it will be encoded once and decoded millions of times. For the typical AI-enabled use case, you encode once and decode once, basically. Or another way of looking at it is, whereas here you need only one encoder to serve millions of users, here you will have maybe millions of these devices that all use a single decoder to complete the task.
Okay. And because you're sending a much smaller sample, the bandwidth is reduced between the mobile device and the network.
Right.
Okay.
So here, just to maybe show first how these things work, what we are showing is 4 examples of input video. In the top left corner, we have uncompressed video. So if you just take this video, don't compress it at all, and then run the convolutional network on that video. Here we have, if you take the input video, compress it with VVC, and then encode it, decode it, and run it through convolutional neural network, doing the object detections. In the bottom left, we have the VCM, the video coding for machines. So again, you take the input video, you push it through the VCM codec, and then feed it to the convolutional neural network. And finally, in the bottom left, we have the FCM, where you take the input video, you push that video through the first part of the neural network, and then you encode with FCM codec these features, decode them, and feed them through the convolutional neural network. So the couple of things to notice here is that first, you can see what is the bitrate needed to transmit this video. VVC here will be encoded at 319 kilobits per second on average for this sequence, VCM at 175, and FCM at 154. Now, just a point of emphasis here for your viewers who are used to looking at the comparisons between traditional video codecs. They shouldn't focus here on the video itself, because video itself here is just the copy of the uncompressed video. We are comparing here from the point of view of a machine. So we are comparing the detections. What is the precision of the detections of the machine? And as you can see here, uncompressed video has, of course, the ground truth, the best detections. And then you can see that VVC, although it's using more bandwidth than VCM and FCM, is lacking some of the detections. VCM is able to detect more at a lower bitrate, but FCM really kind of achieves best of the both worlds. It uses the lowest bitrate and still is able to detect some things that other codecs here are missing. So if we zoom in here to the background, there is going to be one cyclist, a person there, that is occupying a very small portion of the frame. So as you know, when the video goes through compression, these small objects in the frame are going to get quite distorted. And as you can see, VVC at this bitrate, the neural network is completely missing that object because the noise that VVC introduced is just introducing too much interference in the inference of the convolutional neural network. VCM has the same problem. Again, the object in the background is not detected, but FCM actually achieves detection same as for the uncompressed video. So basically lossless compression there would give you the same precision. I want to emphasize here that, as you can see, the confidence of detection of the neural network for this object of person is 99%, and with FCM is 98%. So it's a quite confident, high confidence detection. However, for VVC and VCM, this object is completely missed. So that is quite a bad outcome for some critical scenarios and use cases where detection is kind of like a critical part of the system.
You talked about subsampling the frames down to a very small resolution. I'm not seeing that in these frames. I mean, they seem to be pretty much the original frames. I'm not seeing any lost detail. So what's happening there? And also, are you doing the same for VVC processing with the subsampling? I mean, how did you make these the equivalent if FCM involves so much more scaling?
Right. So again, just to emphasize for your viewers again who are used to looking at the decoded video and looking for details, differences in details. Here, the point is that this is machine is looking at the video, so the only thing that machine sees are those features, and it's giving out the detection. So you can consider these detections as mean opinion scores for the subjective tests for humans. So in order to depict the videos that are decoded, of course, FCM uses features, so you wouldn't see any video itself. It would only produce features. So in order to visualize this for your viewers, we are using exactly the same video, uncompressed lossless video in all four cases, just to basically compare exactly where the objects are in the video. But detections are coming from the neural network that is analyzing the bit stream that is produced by, in this case, VVC, VCM, and FCM. And to your other question, so FCM is subsampling both temporally and especially the input video as a pre-processing. For the VVC itself here, to achieve this 319 kilobits per second, only high quantization was used, no rescaling. Now VCM is kind of, let's say, close to more, I would say it's more close to VVC way of operating than FCM. So VCM is going to use some spatial resampling, and that is how it's going to achieve this 175 kilobits per second. But again, because it's using different type of content, it's producing some basically false negatives.
Okay, so these are not the actual video that is seen by the machine. This is just the uncompressed video with the results from the object detection.
Correct, for visualization purposes, because in the case of FCM, there is no video to be seen, only features are produced, so it would be meaningless to just depict the features.
Okay, good, thank you. So let's review the use cases and the key benefits.
Yeah, so I think I think the key takeaway is that it shifts the paradigm of video coding, right? So from one to many of a traditional video where you encode once and distribute to millions of households and end users playing on devices, right? On one to one and many to one type of a situation base, right? So every sensor is a video sensor is a recording device capturing features, streaming features, right? They're collectively uh, uh, decoded by a single server or a series of servers, right? What have you, right? But this makes the architecture also makes it possible to now scale this compute. Now that you're relying on these millions of sensors to capture and stream the data, why not leverage the compute of these sensors as well, right? In performing this task instead of offloading all this compute and inference to the remote server end or a receiver end, right? You can potentially split the compute. That's a shift in paradigm that we can leverage to scale systems better. And also with technology continuing to evolve, right? These types of accelerators that perform so-called AI accelerators or feature extractors are becoming cheaper to integrate, right? And that we don't expect cost to be a problem of adding these feature extractors to be that significant. That's expected to come down quite quickly to be integrated into all these new class of sensors basically, right? And what this brings you is the benefits of scalability. Now you have a camera, it also not only is capturing, let's say, pixels, it has some accelerator, let's say, to extract efficiently features from it, right? So now you can take those features in a very low complexity channel, with very low bandwidth channels can be leveraged to stream those features, right? So now you can support a lot more sensors in a low resource environment. So it supports lots of use cases in uh, defense, agriculture, autonomous systems, any number of those, right? Where you don't require, where we don't have to use a large bandwidth system, where you may not have access to such a large bandwidth access to stream video, basically, right? So bandwidth efficiency. And and privacy is sort of almost a built-in capability of this FCM, right? Like Velibor pointed out, where you just get a features from it, and for convenience, we overlaid and showed how it would look, right? Receiver doesn't have access to any of the pixel data to, you know, to identify anybody, right? To see the visual details, if you will, right? So it has some obviously details that allows you to detect objects, etc., right? That's sufficient features. That, however, it still gives you a higher level of privacy, right, than looking at an entire picture now, right? If you have an entire traditional video, you know who that is. Maybe with features, you know there are two people, right? So unless you also capture some other related features there. So privacy is a built-in capability of the system.
I guess the counterpoint is, won't this be used for face detection as well? So
I think if you have a phase detection, since features are target and application dependent, right? So if you are doing an object detection, you wouldn't extract features that will allow you to identify faces, for example, right? So it's a you can implement systems where features only serve a subset of applications. Unlike
Okay.
a video, once you capture a video, anybody could do anything with it, right?
So
On the other hand, if you have a pedestrian camera that's intended to just count people, you can ensure that none of the details, identified details, would be there except counting people, right? Because the level of feature detail you need to count people would be very different, right? So that allows you to serve one application and provide certain level of guarantees that only such type of applications would be supported with those features.
what about numbers? Do you have any BD rate numbers or percentage reductions for processing power?
So here's the FCM performance in a standard way presented. A lot of your viewers are going to be familiar with this rate distortion curve, where we have on the x-axis the bit rate at which the bit stream is encoded. And then here, instead of your familiar PSNR or MOS for human consumption, we have this mean average precision score, which gives you kind of like a confidence or precision of how many expected things the machine has detected. So here you can see that we have, in this particular case, comparison with the FCM and the VVC. The curve for VVC is presented here, FCM here, and you can see, for example, let's say that you have a limited scenario where you can you only provide reliably 100 kilobits per second channel for transmitting information. With VVC, that means that your machines are going to achieve around 26 MAP percentage points there. For the same bitrate of 100 kilobits per second, you can see here that FCM will give you more than 40 in the percentages of MAP. So for the same bitrate. On the other hand, if you are requiring, let's say, your system has a critical threshold of 50 MAP to achieve for your task, FCM can achieve that already at 250 kilobits per second. For VVC, you would need here basically more than 500 kilobits per second, and that's reflected here in the at the bottom in the table, where you can see what is presented here is how much less bandwidth or bitrate you need to achieve the same MAP score, so same precision, same level of confidence for your task. So compared to VVC, FCM is using in the random access case 72% fewer bits or 72% less bitrate, and for low delay 57% less bitrate. So if you compare this to usual evolution from video standard to video standard, it's usually asserted that a good benchmark for a new video standard is around 30 to 50% improvement upon the current standard. And here we see that although FCM is still not finalized, it's achieving these very good results. Now, in terms of complexity, of course, being that the standard is still under development, the codec is not optimized. However, I have to say that actually our team was able to put together optimizations, and we are able to basically achieve, to best of our knowledge, first in the world, real-time FCM coding and transmission. So that's something that we will be rolling out and showing to the wide audience in the coming weeks and months. But I would say that's a very important milestone, because usually when the standard is developed, after it's finalized, it needs some time for the reference software to be optimized to the point where it supports the real-time operation. So I would say FCM in that regard is in a pretty good shape.
What's the platform for real time? Is that a GPU or CPU?
Yes, it's GPU. So the whole idea here for FCM is that it's going to use neural networks also in the operation of the encoder and decoder. And now there is a proliferation of these devices, such as neural processing units and graphical processing units, which are still underutilized by traditional coding methods. So now all of a sudden we have a standard that is going to utilize these additional units and allow basically the real-time, very efficient implementation of the standard.
Okay. Where are these numbers coming from? Are these, you passed by a paper a moment ago. Are these from that paper or are these
So these are
updated?
a little bit updated compared to the paper. They are very similar to the paper, but they reflect a little bit more mature version of the standard. So the paper came out in January, and these numbers are from a couple of months ago. And as any standard, the standard evolves, keeps changing from meeting to meeting. But the numbers at this point in the standard are pretty stable.
Why don't you flash the slide with the paper on it so people can, I guess you need to go the other direction. Okay. Why does the accuracy only go up to 50% in the rate distortion chart that you're showing? I would have thought it would go up to 100%.
Right. So unlike the traditional
Can you
video
go?
coding,
Can you go back to the slide, please? Go ahead.
so that's an interesting question because traditionally you expect certain level of performance that is close to 100%. However, in some of these cases, you need to take into account that that's analogous to some people cannot perceive certain differences in PSNR. So the PSNR wouldn't really go, or MOS wouldn't really go to the full scale of 1 to 5 or 1 to 10. Here we have a neural network that intrinsically is not capable of detecting all the objects. So we are not changing the convolutional neural network, which by itself on the uncompressed input image cannot perform to the 100% MAP. So basically here, if we plotted additionally to this the line that would represent the performance of the network on the uncompressed lossless image, it would be around 55 or 60 MAP. So that's the reference point. The reference point is not 100 because most of the neural networks are not capable of recognizing all the objects in the input video.
Okay.
Yeah,
Let's
that's
go.
the limitation of the networks used to do the detection in this case, basically.
Okay. Let's go back to the block diagram. I think it's 2 slides up. So walk me through that.
All right, so here is the block diagram, your usual codec diagram where we have encoder on the top and then bit stream and the decoder at the bottom. So as we can see here, the input to the encoder proper FCM are the intermediate features. The features then go to the module that is doing temporal downsampling. So it turns out that in order to do well, the task network doesn't need, let's say, 30 frames per second. It can drop off every second or third or fourth frame, then interpolate them on the decoder side and still perform pretty well. So temporal downsampling is the first component. And then we have here another component, which is called a multi-scale feature fusion. And this component is comprised basically of type of autoencoder, which is taking these feature maps, of which there can be many, in some cases 256 feature maps of various resolutions in the different layers and levels of the neural network, and is compressing them all to the latent representation, which is this very small output feature map. And then all of these feature maps then are packed into a frame that is going to be passed to the video encoder. Now here we have packing of the features into a frame, and then we have quantization. Now during quantization, which is a 10-bit linear quantization, in order to basically reduce the range of the features, which are usually 32 bits, to the 10 bits that is supported by, in this case, it's going to be VVC. The quantization is done, and then there is also the so-called refinement of the features, which is a very important component of the FCM codec, and to which we basically were the contributors, which is our invention and contribution. Then this is passed to the feature encoding, which again currently is a VVC encoder, but as we are talking, the MPEG meeting is ongoing in the Korea, where the new basically ideas are discussed and evaluated, and there are some proposals of some other types of encoders, such as neural network encoders, which are also under consideration. So currently the inner codec used here is VVC, and then that's producing bitstream, FCM bitstream, which on the decoder side just goes through the steps of inversion of all these operations.
Okay. Which part is FAU contributing here? You talked about the quantization stage, or where do you fit in to that block diagram?
So we've been FAU's role, right? We've been part of the FCM development right from the beginning, right? So we've been actively involved in developing and contributed to all stages of these boxes. But core of our contributions are in feature conversion stage, right? So that's where our technical proposals are. But standard development includes a number of components, right? And we been, proud to be part of uh, being active in this, right, and having made like significant contributions to the advancing the standard.
Okay. And when you talked about the other standards you had worked with before, was FAU also participating with VVC? And
Yeah, so FAU, right, we uh, been working with OP Solutions. OP Solution is sponsoring our ongoing research in this space, right? So we partnered with them in developing the uh, technology. We worked in technologies related to VVC, and now since 2020, we've been right around the time VVC was wrapping up, we started work on video coding for machines, basically, right? That and ongoing, right? So that has since evolved into VCM and FCM, right? And we continue to develop and contribute to that standard, right? Just to kind of highlight a bit around that, right? So we started around 2020 with this machine to machine, but that, as you know, the standard development process, right? It takes multiple cycles, right? So we collaborated with Interdigital on a joint call for proposal, right? We responded to MPEG's call for proposals to develop FCM. So these responses form the starting point of new technologies, basically, right? So these technologies, call for proposals, are used as a starting point, and every meeting that happens every quarter, right? 4 meetings a year in MPEG, new technologies are proposed, right? Evaluated, iterated over, and continues to develop over multiple cycles, right? So when a new technology is proposed, right? So they're cross-checker. Somebody else has to evaluate it, not just you, but some other partners, participants as well. So it's a very interesting and collaborative development cycle, and we are excited to be part of. Right, we're collaborating with a number of partners in this collaborative development, right, and uh, we have made some really exciting contributions that are at the core of FCM, right? That's advancing FCM today.
okay, where is the standard in terms of finalization?
So MPEG, so current timeline is it's expected to go to CD or a committee draft, right? It's considered like a relatively stable version of standard in October 2025. That means core of the development is done. Sometimes maybe small additions could be made between committee draft and draft international standard, right? So DIS is going to be January 2026, right? And followed by usually two meeting cycles would be a final draft international standard when that will be published by ISO a little bit after that, right? At each stage, there is a traditional standardization process of balloting, making any corrigenda or any corrections, right? That needs to be addressed. All of that happens, right? But I would say core of the FCM development is now done, right? And since we've been very active participants in the standard, we've been working in parallel on developing real-time implementations, right? That's why we're able to quickly now already put together a real-time implementation running on a GPU, right? And that also drives our, partnerships with OP solutions in commercializing this.
What's the timeline for commercialization? When I guess you can't do, what can you do before July 2026?
Yeah, I think I would say, in this commercialization effort, I would say OP Solutions would be leading it. FAU as a university, where partners will help and enable them to provide technology and facilitate the commercialization of it. But given our close involvement of FCM, I would say we are more or less aligned with standard timeline, which means since we already have a real-time implementation, we are pretty close to having a deployable or a sellable product by the time standard is released in July 2026, I would say, right? Since we already have a real-time implementation and we actively participate, every meeting we go, every improvements that are made, right, we'll be able to quickly bring that back into our real-time implementation, right? So we continue to develop that as a standard evolves, right? We don't have to wait until everything is finalized before we start implementation. See, that's the benefit of knowing the technology in and out as a contributors, and also being part of closely developing team, right? So commercialization, I would expect through OP Solutions lead in this, right, would coincide with standard development. My understanding is in second half of this year, OP Solutions is planning to raise some funding around that, right? And we'll be happy to facilitate as a technical team that that has been working on this. Will be active partners going forward to helping them translate that as well, right? And part of these efforts, right, would be engaging with uh, partners, right? Essentially, sales channel essentially refers to here, I would say, a new industry partners who may have opportunities to define where the product goes, right? As they define where the product goes, they may have insights into what additional features may be needed, right, into FCM to continue to evolve the standard, right? So we expect FCM will add a little bit additional capability, more advanced capability to continue to evolve in the FCM 2.0. And that's where I think these new partnerships will come in handy to uh, continue to advance the standard, right? To make it, to make it most useful, right, and meet industry needs.
What are the applications you're seeing as the ones most likely to be?
I would say some of the early applications, right? So, as we mentioned, automation, industrial automation, autonomous vehicles. I think public safety and defense is another huge sector that would benefit from this, right? So especially for DoD applications, right, where they are monitoring remote locations for safety purposes for a number of different reasons, right? Uh, Remote agricultural monitoring type of applications, infrastructure monitoring, right? Another unexplored and hugely potential area is healthcare applications, right? When you have a sensors monitoring if somebody has a confidence that it's a lot more private, right? People are likely to use it, a privacy protecting camera, than put a camera in their home to observe what they're doing, for example, right? So healthcare, public safety, right? An overarching, I would say, is a smart cities. I think a number of things will come together in these smart cities applications, right? That would include uh, foot traffic, pedestrian traffic, where people are going, right? Crowd control. All of this will become more efficient, much smarter with these types of infrastructure, right? Than currently streaming large number of cameras into a central monitoring station with people behind or analytics remotely, etc. Right? Imagine all of those thousands and thousands of cameras in cities now already pre-analyzing data, right? Video and sending you very quickly, right? Digestible feature set, right, to make you real-time decision, right? That will enable really new class of applications that's not possible today, I would say.
Okay. And this will be subject to some kind of pool-based royalty, as we saw with VVC and HEVC.
Yeah, I think that's a possibility, right? So because the lot of camera vendors will be implementing this technology as in addition to the service provider, right? So pools have worked, I would say, relatively well, right? So in deploying standards-based codecs, right? Yeah, that seems, that yeah, that's a likely scenario, right? That's one possibility. Yeah.
Okay. Well, listen, gentlemen, I appreciate you taking the time today. It's an extremely interesting technology. I've been pushing machine to machine for a long time. It's nice to see it come to fruition.
Yeah, Johnny, I would just like to say we will be attaching this paper with this talk that people can go and download and look at. And we are very happy. It's one of the first papers that explains FCM and how FCM can be used to enable all these use cases. It's a paper that in January at the IEEE's International Conference on Consumer Electronics, which is held every year in Las Vegas in conjunction with the CES. And we are happy that it got recognized by peers and given the Best Presentation in Audio-Visual Systems Session Award. And would definitely want to give a shout out to our great PhD students and researchers, Imran, Juan, and Ashan, who are currently, while we are talking, attending the MPEG meeting and contributing actively to FCM. So that's something that I think is useful maybe for your viewers and audience as a starting point to look at FCM and how it can be used.
Okay, very good.
Yeah.
We'll have that.
Thank you, Jan. I'm really excited to be part of it. Finally we get to speak with, Jan Ozer. We have watched a lot of videos and we have followed quite a bit of your work, and it's exciting to be part of your session. So thank you for having us today.
My pleasure. Good to meet you both, and congratulations on your work so far.
Thank you.
Have a good weekend.